All right. Good afternoon, everyone, and thank you guys for being here. We're going to get going on our session for today. It's now about 3 minutes after the hour. Got a nice full room, and we're going to get started. So, Happy New Year, everybody. Welcome to our January 2025 installment of ENERCALC Office Hours. If anybody's been attending for a while now, you know we transitioned from our sessions platform to Zoom. So we have just a couple of quick housekeeping items before we get going on the program today. So I want to start with a quick sound check. If you direct your attention to the bottom menu, the Zoom window in your browser or desktop app, you can see the chat tool. If you're able to hear me just fine right now, go ahead and give us a thumbs up or an okay or a reaction emoji of some kind in the chat. Let us know that your sound quality is just fine. Just take a second to do that from everybody. Make sure that you can hear me okay. All right, perfect. Thank you guys for confirming that. And then before we get on to our other items, we also want to do a quick sound check for our primary speaker today. So once again, if you can hear Derek's voice here in just a moment, go ahead and give us another thumbs up or give us an okay, smiley face, whatever.
Hello, everybody. Can you all hear me?
All right, good deal. Thank you guys for helping us out with that. Now that we have our tech checks out of the way, we are going to go ahead and disable the chat, and we'll move on to some introductions and get going with today's program. We'll talk about Q&A at the end. So my name is Seth Roseworm. I'm a senior structural engineer and software developer here at ENERCALC. Our presenter for this month's ENERCALC Office Hours is Derek Serino. Derek's a structural engineer here at ENERCALC, and he splits his time between tech support and engineering support for our customers, working with the ENERCALC engineering team and software developers on the specifications and technical behavior of our software, as well as helping maintain a presence for ENERCALC national and regional events throughout the U.S. So prior to joining ENERCALC, Derek was a structural engineer practicing in the San Francisco Bay Area for about 9 years. He's a licensed structural engineer and professional engineer in both California and the state of Washington. As a practicing engineer, he worked on a wide variety of different projects, everything from schools to fire stations, commercial structures, office buildings, apartments, seismic retrofit, and even some large-scale sculpture structures. So for anybody who's new here this month at Office Hours, the idea behind Office Hours is to provide simple, direct line of communication between you guys, our users, and us. It's meant to do multiple things. We showcase a lot of new features and updates from ENERCALC, showing you guys what's new, what's happening with the product. We answer questions submitted previously in writing from our customers. We do live Q&A, hands-on examples, and then we also do deep dive feature highlights on specific individual modules. If you ever have a question that's too involved or requires deep digging and research, that's usually a better fit for our support team, and we'll be sure to let you guys know if a question that's posed during the session is outside the scope of what we're able to cover. As a minor point of order, you will notice that everybody's microphones are muted just to make sure we don't get any echo or feedback during the session. As I mentioned, we do have open Q&A at the end of every session, including today's session. So to submit a question for today's Q&A, just go ahead and use the Q&A dialog in the lower dashboard of your window. If you experience any audio problems at any point during the session, you can simply refresh your browser or get out and rejoin the session. You also have your native Zoom audio controls. If you ever want to rewatch today's program, watch one of our previous Office Hours programs, or share it with someone on your engineering team, all those recordings are posted to the Office Hours playlist on our YouTube channel, and they can be accessed from the Office Hours page on our website. So with all that out of the way, I'm going to go ahead and hand it over to Derek to get us going on our program for today.
Awesome. Thanks, Seth. Hi, everyone, and welcome to another session of our monthly Office Hours program. As Seth said, my name's Derek, and I'll be your presenter for the day. So I'd like to start our session with a brief overview of today's agenda. So we'll be covering how to make sure you're using the latest and greatest build of ENERCALC. Then we'll talk a little bit about what's new in ENERCALC, and we'll move on to today's design spotlight, which will be on the concrete beam module. We'll also discuss how to register for Office Hours so that you are notified for our future learning sessions. And then we'll wrap up with the live Q&A, so please feel free to drop your questions in the Q&A forum throughout the presentation. So first, I'd like to encourage you all to check your software to make sure you're on the latest build of ENERCALC. If you just take a minute, open up your software, and you'll see the current build at the top of the program. We do release monthly updates, and we want to make sure that you're taking advantage of the newest features and program capabilities. We commonly receive support questions from users where, a user may not see a certain feature, or maybe their hand calc isn't matching the program output. And in many cases, this is just resolved by us identifying that they're on an old build and having them update to the newest build. So I'm going to walk you through that real quick here and also show you how to get notifications for new builds so you can make sure you're always staying up to date. So at the top of your program, there is an update button in the upper ribbon. And if you click that, you'll get this window where you can check for updates now, or you can launch the 4-hour users page where you can download the updater file for the latest build. If you launch the 4-hour users page, you can also install the latest build update under the software download section on the website. Once that's downloaded, you can launch it and run it, and then you'll be running on the latest and greatest build. If you'd like the program to automatically check for updates at program startup, you can also click this checkbox here. A quick note for users on builds 2023 0830 through 2024 0228, the feature which notifies you of the availability of new updates doesn't function properly. So if you have automatically check for updates enabled and you haven't been notified about new updates in quite a while, there's a chance you might be on one of these affected builds. So to fix that, you'll just need to perform a one-time manual update, either from inside of ENERCALC or through the website, like I just showed you. And as of today, the latest build is 2024 1217. And if you'd like to be notified of the latest ENERCALC updates by email, you can scan this QR code or sign up at updates.enercalc.com/subscribe, and you can provide us your email there. And once you do that, you'll receive email notifications whenever a new build's released, and those emails also include highlights of notable updates. Each email also includes links to the full changelog at updates.enercalc.com for those of you that are interested in a more detailed breakdown. Now, if you haven't been on the latest build or maybe haven't had time to poke around in ENERCALC recently, I'd like to highlight some newer features and functions that you can take advantage of here. So first, let's discuss the decoupling of IBC and ASCE editions. Some jurisdictions started mixing and matching design standards. So for example, your jurisdiction may adopt IBC 2021, which refers to ASC 716, but it may have some state-specific amendments which reference the ASC 722 instead. Previously, ENERCALC lumped the ASC edition under the IBC that references it. So for example, if you were using IBC 2021, ENERCALC would by default use ASC 716 as referenced by that IBC. And now after the decoupling of the IBC and ASC editions, you can use whatever IBC and whatever ASC combination works for you, which gives you just a little bit more flexibility to meet your jurisdiction's requirements. The second update is the addition of new ASC 722 modules. Previously, all projects came preloaded in with the various loads and forces modules for ASC 716. And now these loads and force modules behave similarly to all of our other modules in that they can be added, copied, deleted from any project. So you may have noticed the add module window now has 3 additional new tabs. First tab is the seismic loads tabs, where we added calcs for seismic base shear, seismic wall anchorage, and seismic demands on non-structural components. Next tab is the wind loads tab, where we have calc modules for ASC 722 wind forces per chapter 22 and chapter 28, as well as ASC 722 wind enclosure determination. The module for components and cladding per chapter 30 is in active development, and that will live here once it's been released. And the last tab is the other loads tab, where we have added a calc module for ASC 722 live load reduction. Any additional calculation modules for this tab, such as snow loads, will live here once they've been released. So another relatively new feature is load linking natively within ENERCALC. So load linking gives you the ability to automatically link reactions from one calc to another, and the ability for you to change something in one member and then have those effects of that change trickle down to all of the supporting members. So this is one of our most requested features from users, and we're excited to say that load linking is available currently in steel beams and ready for you all to use. Load linking for the other modules is in active development, so make sure you're staying up to date with the latest builds so you can use those new features as they roll out. So let's jump into a steel beam calc and see how linked loads can streamline your workflow. In the steel beam calculation module, you'll see a new tab at the top called linked loads. And on this tab, you can grab reactions from other steel beam calculations you have in your ENERCALC project file and apply them to your beam as applied loads. So as you cycle through the calculations, you get a 2D diagram of the member just to refresh your memory, and so you can have confidence that you're choosing the right reactions from that member that you're going to be linking. And then at the bottom of the 2D sketch, you'll find a table which shows you the reactions that you can grab from each member. After you select the beam you want to link, you can then determine how you want the reactions to be applied to your current member. So for example, once I select beam number 1, I can choose to apply the load at midspan, third points, quarter points, specific spacing, specific locations. So you can see here that I've chose to apply the beam number 1 reactions at 1/3 points. And once I'm happy with my selection, I can click the add button and I'll see the linked reactions in the table below. All of the linked reactions for the current calc will appear in that table. So for example, we can see the placement is at 1/3 points, and you can see clearly here in the 2D sketch that the reactions are applied at third points. Now, if we look at the corresponding changes in the project manager, if you're in the latest build, you'll see a new tab at the top called Calc Order. So this tab just organizes all of your calcs based on the load path order. So you can see beam number 1 here is listed first, and then the primary girder, which receives reactions from beam number 1, then the transfer girder number 1, which receives reactions from the primary girder, and finally the transfer girder number 2, which receives reactions from transfer girder number 1. You can link multiple reactions from multiple members at the same time, and ENERCALC will understand the load path logic, ensure that all calcs are performed in the proper order. And at the bottom of the screen here, we can see the load linking status badges. These just help you better understand the status and warnings of each calc. So it's important to note here that these status badges do not indicate the pass-fail status of the beams. They just serve to help you determine if the calc with linked reactions is up to date. So for example, if we were to look at, if we were to update the loads in beam number 1, we would see the linked load status badges for all of the downstream calculations turn orange and red, indicating to us that a recalc for those members is needed. And then you'll also notice a new button on the top labeled Recalculate Linked Loads. If you don't want to go through each calc one by one to observe the changes caused by those updated reactions, this button just allows you to bulk recalculate all of the calcs to ensure that the most up-to-date reactions are being used and their effects are trickling down to all the related members downstream. So you can see how load linking is pretty powerful and intuitive and helps you create a well-connected chain of calcs while also minimizing the risk of transcription errors. And that was just a pretty quick preview of load linking. If you'd like more info, you can check out the load linking playlist on our YouTube channel. This playlist walks you through how to use load linking step by step. The first video's got a full overview. The second video has a walkthrough of a short example, and then the other videos kind of dive a little bit deeper into all the various functionalities, which I just breezed through here. You can give this playlist to anyone, someone who's never used load linking or a new engineer, and they should be able to follow along with the instructions and best practices of how to use it. And then the final new feature I want to highlight today is our ENERCALC for Revit full gravity load path. So if you attended November's office hours session, Seth took us through ENERCALC for Revit, which is a Revit plugin that allows you to leverage ENERCALC to design structural members fully within Revit without the need to export a stick model or export info to some other calculation software. And we previously supported steel beams, steel composite beams, and wood beams. And now steel columns and general spread footings have been added as well, which completes the full gravity load path for steel structures. So let's take a look at this in action. So here we have our Revit model, and we can navigate to the ENERCALC cell tab in the ribbon bar and select steel column design. You can then pick the steel column you want to design, confirm the gravity support conditions. We can specify the slenderness inputs in both the X and Y directions by either selecting the full column height or by directly picking the bracing elements from the Revit model. We can then confirm our tributary loads from the adjacent framing elements. And once we click OK, the program will open an ENERCALC calculation with all the info from Revit pre-populated. So I can give the column a name here. And then we can see the column size was brought in from Revit, and the applied loads, which are based on the reactions from the tributary elements framing into the column, are brought in as well. Once we click Save and Close, we'll be taken back to Revit, and the column size will be automatically adjusted to match our calculation. So we'll see that here. We can also use the same point and click logic for the foundation as well. So we select our footing and confirm the tributary column. We can then give our footing a name and update the material properties and soil properties. We can see the reactions from the tributary column are automatically populated, and we can also adjust the footing geometry and reinforcement in the ENERCALC calculation. And once we click Save and Close, those calculations will be carried over to Revit. So the Revit model will automatically update based on those changes, and the reinforcement info will be added as a property, which we can then use to tag in our construction drawings and schedules. So if you have an active ENERCALC for Revit subscription, you can update to the latest EFR build by going to the 4-hour users page and downloading the latest build, just like you would for ENERCALC Cell. So that covers today's What's New portion of the session, and it's time to move on to the design spotlight. The focus of our session today is the design of concrete beams using the concrete beam module in ENERCALC. So we'll cover the module's capabilities and limitations, walk through an example together, and then we'll jump over to the live Q&A. The concrete beam module can handle a variety of beam configurations, whether it's single span, multi-span, cantilever beams, and it also has the flexibility to accommodate various support conditions. It also supports a wide range of beam shapes and offers fully customizable reinforcement layouts. It can also calculate immediate deflections for both total and transient load conditions while considering crack section properties through effective moment of inertia calculations. So for today's example, we've been tasked with designing a 2-span concrete floor beam designed per IBC 2021 and ACI 31819 in seismic design category C. Both spans are 20 feet and the trib width is 20 foot as well. The beam is supporting an 8-inch slab, and for the sake of keeping things simple, I'm not going to assume an effective slab width here. I'm just going to assume a simple rectangular beam, not a T-shaped beam. So the 8-inch slab comes out to 100 PSF of applied uniform dead load. And we'll assume there's another 10 PSF of superimposed dead load for finishes, MEP, etc. The beam is supporting a typical office occupancy with interior partitions. So we end up with 110 PSF of dead load and 65 PSF of live load. So let's jump into our ENERCALC program and start a new concrete beam calc by clicking Add, navigating to the Beams tab, and selecting the concrete beam module. I always recommend starting with our inputs in the General tab and then working your way through the inputs, moving left to right as we set up our calculation. So here on the General tab, you can give your calc a unique name, and you can see I've named this one B1 Continuous Concrete Beam. And then we can jump down here into our material properties. So on the left-hand side, you can specify the concrete strength and density. I'll just be using 3000 PSI normal weight concrete for this example. And on the right side, you can specify the strength of the primary flexural and shear reinforcement. I'll be using A615 grade 60 bars for both flexure and shear. And you can also specify the size and number of legs for each stirrup. So I'm just going to leave this at my default of 2 legs of number 3 bars for now. But we can always update this later to optimize our design. A quick note regarding default values. ENERCALC allows you to set default values for parameters in all of our modules, such as F prime C, FY, the fee values, and so on. Throughout our example today, I'll be referring to the default values that I've set up in my program, but if you're following along in yours, you might notice that some of your defaults are different than mine. You can always modify your default values in the Settings tab. And if you need a refresher on this process, Mac walked through this in detail in July's office hours presentation, which you can find on our office hours page. The default values portion of the video starts around 16 minutes and 25 seconds. So if we jump back to our example, we can define the fee factors used for both flexure and shear design. By default, ENERCALC assigns a value of 0.9 for flexure. This aligns with section 9331, which specifies that non-pre-stressed beams must be tension controlled as outlined in table 21.2.2. The tension control requirement just ensures sufficient ductility for which warning of failure by excessive deflection and cracking can be expected. And according to table 21.2.2, a tension controlled beam receives a fee value of 0.9. If the beam is over reinforced and does not meet the criteria for being tension controlled, a warning message will be displayed to alert you so that you can avoid some brittle failures. For the concrete modulus of elasticity, the user can either manually input their value or they can use one of these buttons here provided to calculate the modulus based on the F prime C input above. Note that if you change the F prime C value, you'll notice that the modulus does not automatically update. So you must either manually input the corresponding modulus or reselect one of the buttons to have the program recalculate the new EC value based on the updated F prime C value. I'm going to use the far left button here to determine my modulus of 3,122 KSI for our 3 KSI concrete. And here we can specify the minimum deflection ratios for both transient loads and total loads, as well as the deflection calculation method. Note that only immediate deflections are calculated in the concrete beam module, so all time-dependent deflections must be evaluated separately. And if I jump back up to the top here, I've specified a seismic design category of C and uncheck the box, which indicates that this beam is not part of the seismic force resisting system. And a couple things I want to note here as well. Concrete beams falling within seismic design categories D, E, and F are beyond the scope of this module. Beams in those seismic design categories are subject to additional design requirements outlined in the ACI, sections 18.6 for SFRS beams and section 18.14 for non-SFRS beams. And for those cases, ENERCALC will suppress the results since the program is unable to ensure compliance with the ACI code requirements. SFRS beams in seismic design categories B and C are governed by sections 18.3 and 18.4. And for those cases, results will be displayed, but you'll still see a warning telling you that you need to separately confirm some additional detailing requirements specified in those ACI sections. So if we jump back to our example, since our beam is in seismic design category C and not part of the seismic force resisting system, we can proceed and move on to the beam span data tab. So at the top of this window, you'll notice where we can specify the beam dimensions. And this is where we can select which span the data entry values are applying to. Additionally, we can define some critical dimensions like span length, beam height, and beam width. I've entered the span length of 20 feet here from our example problem. And in practice, you typically start with an assumed size, you check the design, and then adjust the dimensions iteratively until you find a solution that you're happy with. So to save time here, I've already gone through that process and settled on a beam size of 24 inches tall by 16 inches wide. This module can also handle a variety of beam shapes as shown here. So for simplicity, like I said earlier, I'm just going to be sticking with the standard rectangular section for this example, but you can always pick from any of these shapes for yours. Whatever section you do choose will remain consistent across all of the spans. The beam section that's displayed here is a single cross-section cut at a specific location along the beam, and you can adjust the section cut location if you want to preview the reinforcement layout at different points along the beam. So for example, at 0 feet from the left to end, we can see this cross-section with bar sets number 1 and number 4. That is the blue and black bars there. And if I update the section cut to 12 feet, for example, the section cut indicator updates And now we see a new section, a new cross section with bar sets number 1, 3, and 4. So that's the blue, purple, and black bars there. At the bottom part of the beam span data tab, we can define up to 6 rebar sets. Each set includes the quantity of bars, their size, their vertical positioning, and the starting and ending locations within the span. So these color-coded dots here to the left of each rebar set are just a convenient reference, which match the schematic beam section and elevation sketches shown here at the top of the screen. And then here you can define the quantity and size of each bar in each set. The section here labeled distance of bar center from defines the vertical positioning of the bars relative to the top or bottom face of the beam. Note that these distances are measured to the center of the bar. They are not clear cover distances. So make sure you're accounting for those distances appropriately. And then here you can fine tune where each rebar set starts and ends within the span. If you want your rebar set to run full length of span, you can click these FL buttons to set that automatically. And also note that the module will issue an error if any part of the beam is completely unreinforced. So it's important to make sure you're ensuring proper bar extents, especially at the beam ends where rebar is often terminated. I also want to make a quick note about rebar development. So the ACI includes detailed requirements for rebar development lengths in section 9.7.3. And as you can see here, there's quite a few of them. Within this module, bars are always assumed to be fully effective at the points where they're defined. So what this means is that the rebar sets are assumed to be fully developed at the defined start and end locations. And this is evident if we take a look at the moment diagram. So here you can see the various moment demands along the length of the beam for each load combination. And you can also see the flexural capacity curve highlighted in red on the screen here. If you look at the purple rebar sets at the bottom of the beam in the middle of each span, we can see that there's a bump in positive phi mn capacity. And this starts and ends exactly at the start and end of the rebar set. And then we can see similar behavior if we look at the green rebar set at the top of the beam at the interior support. So it's essential to understand that behavior and make sure that you are accounting for any additional development links on your construction drawings to ensure that the bars are fully developed at the locations where you need them to be. So just remember, this module is an analysis tool. It's not a detailing tool. Fortunately, the ACI commentary offers some pretty helpful diagrams to help guide you through these checks. So if we jump back to our design example, as I mentioned earlier, designing reinforcement in practice usually involves an iterative process, adjusting and tweaking the layout until you've reached a solution that you're happy with. Like I said, I've already completed that process ahead of time, and I've settled on the rebar layout shown here. And since our beam configuration is symmetrical and the loading is uniform, I've gone ahead and mirrored the rebar layout for the second span as well. Next, we can move on to applying the beam loads. The span loads tab is where we define the loads acting on our beam. These are applied on a span by span basis, meaning each span of the beam can have its own unique set of loads. This tab probably looks pretty familiar. It's identical to the span loads tab in all of our other beam modules, which Mac has already covered in detail in previous office hours. Since the beam in our example has only uniform loading across all spans, I won't actually be using this tab directly for our example, but I will give you a quick overview of its features. So at the top of the tab, you'll see some buttons where you can select the span you want to assign the loads to. To begin, you just click this add button here to create a new load. And then from there, you can define the type of load. You know, if it's a point load, uniform, trapezoidal load, point moment, you name it, and the load magnitude, as well as the distance values. And then you'll also see some helpful automated features. So first here is the auto add beam weight option. If you enable this, like I've done so, this just automatically includes the self weight of the beam as a uniform dead load, which is based on the beam's dimensions and the concrete density, which we specified on the general tab. And then next we have this auto unbalanced live load placement option. This feature just generates all of the possible unbalanced live load permutations across all of the spans. So I've gone ahead and enabled that as well. Note that while this is incredibly useful, especially for multi-span beams, it's worth noting that enabling this option does increase calculation time, particularly for beams with more than a few spans. So just keep that in mind. And as mentioned earlier, since the beam in our example has uniform loading across all of the spans, I'm actually going to be using this Loads All Spans tab. So to start, I define the load type as uniformly distributed. And then I input the 110 PSF dead load and the 65 PSF live load. And I also specify the 20-foot tributary width from the problem statement. So once I've defined those inputs, I can check the 2D sketch to see how the uniform area load has been converted into a uniform line load of 2.2 KLF dead and 1.3 KLF live. And while it's not necessary for our example, I also want to point out an additional feature of this Loads All Spans tab. It does allow you to define repeating loads at the bottom of the window. So for demonstration purposes, I've defined a point dead load that starts 4 feet from the left end of the beam and repeats every 6 feet on center thereafter. And if we check the 2D sketch again, we can see this repeating load represented visually. As I said, this is just for reference. I'm just going to go ahead and remove those loads from our design example. And finally, we can take a look at the load comms tab. So this is where we define the load combinations that we use for strength, reactions, and deflections in the calculation. Since this tab is virtually identical across all ENERCALC modules, and Mac has already covered it in detail during our previous office hours, I'm not going to spend any time going over it here, but just keep in mind that this is your go-to tab for anything related to load combinations. And now that we've fully defined our beam's properties, the dimensions, loading, and reinforcement, we can review the results. So the calculation tab provides several result options, and there's a lot of interesting results on all the subtabs contained within, but I'm just going to dive into a few of them in more detail here. Starting with the summary results tab, this is probably the results tab you'll be looking at most often, as this provides the governing results for bending and deflection. And while shear results aren't shown here, they are summarized on a separate tab, which includes the required stirrup layout to meet shear demands. But we'll be talking about that a little bit more later. So here we can see the maximum bending stress ratio along with the governing moment demand, the location of the maximum moment, the phi mn value at that location, and the governing load combination. At this stage, you typically review these values and confirm that your design works. And if not, you'd go back and adjust your section dimensions and reinforcement layout until you have a design that satisfies your requirements. In our example, I've already done that work of iterating through different section dimensions and layouts. So the layout I showed earlier achieves a 91% demand capacity ratio, which I am happy with. And then below that, we see the deflection ratios for both transient and total loading. It's important to note that what's reported is not necessarily the maximum deflections, but rather the maximum deflection ratios and their associated deflections. So the distinction is subtle, but if you're concerned about absolute deflections rather than ratios, you'll need to interpret the results accordingly. And then finally, at the bottom of the section, we have the extreme reactions at each support for each load case. And if we jump over to the MVD summary tab and then the LRFD shears and moments sub-tab, we can see a more detailed breakdown of these results, including moment data for each station along the beam for each load combination. All right, it sounds like my audio may have cut out. Can you guys hear me?
We can hear you now, Derek.
Yeah, we got you now.
Okay, not sure what that's about. I'm gonna start that over. So if we jump over to the MVD summary tab and then the LRFD shears and moments sub-tab, we can see a more detailed breakdown of the results, including the moment data for each station along the beam. So for multi-span beams with automatic unbalanced live load placement enabled, like I've done in this example, this can generate thousands of lines of results based on all of those loading permutations. So just keep that in mind. And in addition to these detailed strength results, this tab also includes intermediate calculations for minimum steel reinforcement. This is per ACI sections 9612 and 9613. And here we evaluate the equations A and B from section 9612, which states that AS min must be greater than 3 root F prime C over Fy, and AS min must also exceed 200 over Fy. We can then calculate the reinforcement ratio to meet the flexural strength, which allows us then to check 9613, which says AS min from 9612 does not need to exceed 4/3 of the AS required for strength. And then from those checks, we can determine in the governing rho min and the associated AS min value. And this tab also performs a check for AS max, which is the maximum allowable flexural reinforcement while maintaining tension-controlled behavior. So as I discussed earlier, section 9331 and table 2122, concrete beams must be designed to remain tension-controlled. So this means the beam must achieve the net tensile strain required to provide sufficient ductility and to maintain that 0.9 phi factor, which we specified on the general tab. While the maximum reinforcement area, AS max, isn't explicitly defined in the ACI, we can calculate it by analyzing the strain distribution from the beam section. So in this strain distribution, the tension force provided by the flexural reinforcement is balanced by the compression force in the concrete's compression block. So the tension force is defined by AS Fy, and the compression force using the Whitney stress block is 0.85 F prime C, A times BW, where A is beta 1 C. Table 2122 also specifies that the net tensile strain for grade 60 reinforcement must be at least 0.00507 to qualify as tension controlled. So using similar triangles from the strain diagram, we can relate the neutral axis depth C to the depth of extreme tensile reinforcement dt. And by summing the forces in the x direction and substituting our earlier equations, we can derive this following formula for AS max. So for our example beam, plugging in the relevant values, it yields an AS max of 4.73 inches squared. And as shown here, we can see this aligns perfectly with the module's results. And we can confirm that our beam is tension controlled as required by the ACI. If either the AS min or AS max limits are not satisfied, you will see this warning, which lets you know that you need to adjust your design. But fortunately for our example, the design satisfies both limits without issue. Next, let's talk a little bit about shear design. So the concrete beam module does evaluate beam's shear demands and reports optimal stirrup spacing for incremental stations along the length of the beam. Under ACI 318.19, the process was pretty straightforward. So we could just calculate the concrete shear capacity V sub C for this section. And then we could determine the required shear capacity due to transverse reinforcement V sub S. And then we can solve for the corresponding stirrup spacing S. However, under ACI 318.19, the process isn't quite so straightforward. For us to calculate the concrete shear capacity V sub C, it's necessary for us to know the relationship between the provided AV and AV min beforehand, where AV min is calculated per 9634. The thing is, we don't know what the actual stirrup design is until after we calculate VC. So this kind of creates the circular dependency here in the design logic. And then to further complicate things, if you were doing this by hand, you might initially assume that AV is less than AV min and proceed with equation C, only to find that after applying stirrup spacing limitations, your AV provided now exceeds AV min. which then forces you to recalculate VC using equations A and B. So you can see how this process would be pretty tedious to do by hand, but luckily we have ENERCALC to help us out here. So to handle this, the concrete beam module evaluates both scenarios simultaneously. So it calculates an optimal stirrup spacing based on V sub C, calculated using equations A and B. And then it calculates a separate optimal spacing based on V sub C, calculated using equation C. It then returns the more favorable stirrup design as a suggested spacing. So to better illustrate this process, here's a flow chart that goes into the shear design logic in more detail. I'm not going to go into every detail, but you can see how it first evaluates the concrete shear capacities using all equations from chapter 22. It then traverses two logical branches simultaneously, and it applies the various stirrup spacing limits in both branches. And then it selects the more favorable stirrup design and proceeds to calculate phi V sub n and the shear stress ratio. This flowchart is included in the user manual, and it will also be part of the summary provided after today's office hours, just for your future reference. So if we take a look at the design shear tab, we can see these intermediate calculations providing a clear breakdown of the entire design process. And we can scroll to the right to see that tie spacings for both design branches are calculated, along with the final suggested spacing, which is the greater of the two. Finally, the total shear capacity is computed using the suggested spacing, and the associated shear stress ratio is reported. Some additional notes are also included to indicate which provisions are governing the design. And wrapping up today's design spotlight on the concrete beam module, let's take a final look at the sketches and diagrams. So starting with the 2D sketch tab, this just provides a graphic representation of the beam with reinforcement layouts and extents, span lengths, and cross-sectional dimensions. And then you also have the option to show rebar length dimensions to display the lengths of the defined rebar in elevation. As I mentioned earlier in the presentation, it's important to remember to include any additional development links when documenting this info on your construction drawings. Moving on, we can go to the diagram tab, which allows us to view shear, moment, and deflection diagrams for the selected load combos. Here's the moment diagram for our beam. And as I mentioned earlier, since we've enabled automatic unbalanced live load placement, all permutations of live load skip loading have been evaluated across all spans. So you can see how this results in quite a few combinations, even for this relatively simple 2-span beam. And we can also display the flexural strength envelope by checking this box here. Next here is the shear diagram, and finally the deflection diagram. And then lastly, we can take a look at the 3D tab, which provides a nice 3D view of the beam, including the dimensions, loads, supports, and rebar. And that wraps up today's design spotlight on the concrete beam module. Before we dive into today's Q&A, I'd like to encourage everyone to register for our office hours program to ensure you're receiving notifications directly to your inbox. Oftentimes, the email addresses we have on file belongs to an IT department or an admin staff who manages the office licenses, which means notifications about these sessions might not actually reach the engineers who benefit most from them. So to avoid missing out, I recommend that anyone interested in these monthly sessions register on our website, and you'll receive updates directly, and you can always unsubscribe if needed. These sessions are open to everyone, so whether you're an active subscriber or just exploring our resources online, you can sign up to join us in the future. So with that being said, you can register by going to enercalc.com/office hours, or you can go to our website and go to the For Our Users tab and then get help/support and click on the office hours option from the menu. This will then take you to a registration page where you can put in your contact info. And if you're an active subscriber, please do us a favor by also including your KW registration number. If you're not a current user of ENERCALC, then you can just leave that blank and click submit, and you'll be included on the email list. We also post all unedited recordings of the previous office hours sessions on this same webpage. So if you're looking for an old video or you can't make it to one of our office hours for whatever reason, just go to that page and you can scroll down to the bottom to see that library. And now it's time to open up to the live Q&A.
All right, let's go ahead and dive into it. So our first question, will would-be modules be getting the load linking
So
function
let's see here.
soon? Yeah, so in general, the answer is yes. We don't tend to announce specific timelines or release dates for those features, but load linking is in progress for Woodbeam, and it's our most frequently requested integration for load linking. So that's what the development team right now. And there's actually I don't know that Derek has a visual handy to highlight this right now today, but there is a poll where you can go and vote actually directly inside ENERCALC itself. If you go to your load linking tab, you can toggle over and you'll be able to access a survey and vote about which modules you want to see integrated. So be sure to take advantage of that. Question from Kyle, is ENERCALC developing an updated module that can design concrete beams for seismic design categories D through F? There is not a new module to do that in active development right now at this time. If that's something you're interested in seeing, be sure to reach out to the support team, support@enercalc.com, to submit that as a feature request. That's how the engineering team sets development priorities, is hearing what the users want to see. So be sure to reach out about that. Question from Ivan. Just to confirm, concrete beam design for seismic design category D and E is not supported, even if the beam is not part of the lateral force resisting system. Derek, feel free to jump in with your thoughts on this, but that is correct. At the current time, the concrete beam module outputs will stop you short and not produce design outputs if you're in seismic design category D or above, regardless of the reason. Regardless of whether you're in lateral force resisting system or not. The main reason for that is because of the significant codependency between ACI chapter 18.14 for not in the lateral system, heavily dependent on 18.6 when you are part of the lateral system. So there's a lot of tight coupling between those provisions. Derek, go ahead if you have further thoughts on that.
Yeah, so if it is not part of the seismic force resisting system, it will still output, a DCR and do all the checks, all the usual checks for seismic force resisting beams. But it will still warn you that there's other provisions in the ACI for those higher seismic design categories that you'll need to still verify outside the program.
All right. Next question. Extreme reactions are service load. Can this be printed on the output to make it clear that these are not factored reactions? So, and Derek, again, feel free to jump in if you have thoughts on this, but every ENERCALC module is set up pretty much the same when it comes to the relationship between extreme reactions and the applied loads that you input manually. The applied loads that you input are going to be the exact way that you see the extreme reactions outputted. So if you decide that the loads you manually key in for wind or seismic or something like that are already factored, then you'll be seeing factored results on your extreme reactions. If you put in unfactored service level loads in your applied loads tabs, like your span loads and loads all spans, then that's what you'll be seeing in the extreme reactions. What you see in the extreme reactions display on the right-hand side of your screen is never going to have additional factors applied to it. It's going to be exactly what you manually input. Derek, go ahead if you want to elaborate on that.
Nope, that was perfect. Like Seth said, the reactions that are output are unfactored based on the loads that you've input into the loads all spans in the span loads tabs. So
perfect. There's a general question about code references having to do with annotation on individual inputs as you were walking through the inputs tabs, Derek. That's something where in some cases we have annotation for code references. In some cases there may not be. Definitely feel free to reach out to the support team if you have specific suggestions or feature requests about where you'd like to see more pop-up annotation for sure.
yeah, and we also have I would also encourage everyone to check out the user manual online. If you have any questions, I mean, obviously you can reach out to the support team as well. But if you're looking for an immediate answer, the user manual has a section on the concrete beam, which is pretty helpful. And there's a little more information about the equations and references that are backing up some of those inputs that you'll see on the screen.
All right, next question. Can a shape be developed of edge condition beam L shape, half of a T? So you do have the traditional L beam in ENERCALC right now. There is not currently an inverted version of the L, which would be half a T. Like the question says, there's nothing in active development to add that at this time. You don't have that capability right now to add an inverted version of the traditional perimeter L beam. But again, be sure to reach out to the support team if that's a use case that you have that you feel like you'd like to see implemented in the future. All right. Question from Justin. Due to rebar detailing requirements, we often utilize longitudinal rebar at mid-depth of the beam. This allows for moderate capacity increases while avoiding rebar congestions. Does ENERCALC analyze mid-depth rebar? Or are there any errors, concerns with using mid-depth rebar in ENERCALC?
Yeah, so whatever rebar you define in the on that beam span data tab will be included in those strength calculations. So if you're putting something, based on that strain distribution. So if you're defining the bars, it should be included in the strength checks.
Yeah, for sure. And you would have to be careful of your section geometry and have a good idea in your own mind of what the strain diagram looks like for that reinforced section, because if the neutral axis doesn't fall where you think it does, then that would affect whether your reinforcement is behaving in a compressive manner or a tensile manner for the behavior of the beam. But it is, like Derek showed us earlier, the module is doing a rigorous analysis of the cross section using the strain diagram based on all reinforcement placed in the section. All right, let's see. Will load linking be available from base reactions of columns bearing on beams? So this is a great question. We do hope to have that capability in the future. That's not integrated right now, but again, if that's something that you need to see for your team's workflows, be sure to go to the load linking tab, go through that survey, and go ahead and put your votes in there if you want to see, for example, column base to beam load linking. This is a pretty similar question. Plan to allow for load linking from column module to beam module. Okay, same question. So be sure to go check out that survey for those kind of capabilities. Does the program show the shear reinforcement in the 2D or 3D view?
At this time, it does not. So there's two places you can see the shear design. You can see it on the table that I had showed during the presentation. You can also see it in the project or the calculation report. So if you print a report to PDF, or you do the print preview, there is a summary that's a little more concise than the tabulated output, which will just show you it'll kind of group the spacings into some categories, so you're not dealing with 6.1 inches, 6.2 inches, 6.3 inches, and so on. It'll kind of put them in little buckets, so you have a little more consolidated design, but there is not a way to graphically view that info.
All right, quick question about an unrelated topic to today's session about designing 2D or 3D steel frame with lateral load and so on. We actually do have an email address where you guys can reach out if you have requests for future office hours content, and that's, I believe, just officehours@enercalc.com. So if you have requests or questions you'd like to see featured in a future office hours session, be sure to put those in an email and fire them out to the office hours at ENERCALC address. And that way we can consider that for future content for you guys. That question from Justin, I believe, is a repeat. Justin, let us know if we did manage to cover your question, and if it requires more digging, we can also handle that with the support team as well. Let's see. We're getting pretty close to the end of the hour here. Derek, any plans on adding long-term deflection? You mentioned specifically that the results being reported are immediate deflection. Someone wants to know about plans on adding long-term deflection calcs.
That is not something that we have, active development plans in the works, but it is something that is on our radar, and I highly encourage you, like we've said a couple times already, reach out to the support team at support@enercalc.com and let us know that that's something that you're looking for, because that really drives the development route. So cast your votes by basically emailing us and telling us the stuff you guys want to see in these modules.
All right, great questions. We're pretty much down at the end of our time for today. Again, if there are any questions you guys have that we did not get covered, or if you need to dive deeper on any of those topics, we definitely want you guys to reach out to us. Stay in touch with the support team, support@enercalc.com. Any questions about licensing, purchases, business office type questions, adding seats to your pool of licenses, adding ENERCALC for Revit to your subscription, those kind of things, info@enercalc.com will get you to the business office. And we just want to leave you guys with just a reminder to sign up to get notified for next month's office hours session. We'll have a February office hours. Date and topic on that will be on the website soon, so be sure to keep an eye out for that. And we thank you guys for your time today. We'll look forward to seeing all of you next month.